Hey everyone, this video is meant to help out other content creators with their thermal testing and also explain to viewers why temperature testing with cases, coolers, GPUs is a lot more difficult than it seems on paper. This idea came about when I was watching one of Bitwit's videos, Kyle, about CPU cooler orientation, and it was a great idea. We've tested it in the past, quite a long time ago at this point, and Kyle had some interesting findings where he basically said that, look, here's the data I found, but I don't necessarily understand why the numbers are the way they are because I didn't expect it to be that way. And that approach, just to briefly state here, is perfect. You can't get a better approach than that to science when you're saying, look, I've done the testing, I've done due diligence to make sure it wasn't something weird as far as I know, but I don't fully understand the results. Here's the data, what do you think? That's a great way to approach it because the other options are throughout the data, which you don't want to do because there might be some really valid thing there that he's discovered that's not being discussed, or of course presented as hard fact, which also you don't want to do if you don't necessarily understand the data. So the reason I bring this up is because I have gone through that so many times in the last few years. Thermal testing up until maybe the last year and a half for us has been a major headache. There was a full year where we stopped doing case reviews at all with thermals in them because we were having issues, and then brought it all back after I was able to validate our new testing methodology in thermal chambers and really create some numbers that I finally trusted. And that was a hard process to go through. We've got videos detailing the thermal chambers, we've got videos detailing our temperature measurements, all that stuff. But I want to go through some of the more gritty details today, just as briefly as I can, because this is a Sunday video for us, which means I'm producing it myself. The other two guys are off today. Before getting to that, this is brought to you by our Patreon backers. Thank you to those of you who support us. You can go to patreon.com/gamersnexus to help out. We've got a couple goals there. We've reached one of the most immediate ones, but we're pretty close to the next one. So do check out the site if you want to help out, gamersnexus.net or patreon.com/gamersnexus, and you can support us directly. So before getting into the details here, any content creators or anyone up and coming or established or whatever, if you're using any of the methods that we talk about in this video, give me a shout, because this stuff has been a long time in the making, years and years of work to kind of slowly figure it out, and it's expensive to do, and sharing with competition, obviously. We keep some stuff secret, but I'll put a lot of it out there in this content. Just point folks our way. I would greatly appreciate that. So let's go over some of the stuff on the table. We've got coolers that I've tested, we have tools, we have thermal paste, and we have notes of huge issues I've run into in the past that have invalidated data or caused major headaches that put us back weeks in production. And it's all mostly figured out. I won't put everything we do in this video because one, obviously competitive reasons, but two, there's a lot to do. So our tests are fully automated, which helps. The script is internal only, but you could write your own script if you wanted to. The test environment, there's a few things that really matter here. One is ambient temperature, and we've talked about that in the past. Another one is the BIOS settings. Those are really critical, probably more than any other single aspect of thermal testing. So let's go with ambient temperature first. Room ambient, you want to control the temperature in the room as much as possible. If a thermal chamber is not available, we don't test in a thermal chamber, but we've validated in one, so the methodology is known good. And that's really all we needed for this type of testing. For room ambient, just setting the thermostat is not good enough. So if you set your thermostat to say 20 Celsius, which is about what ours is, there's still going to be fluctuations, and some of it could be from vent in the ceiling. If a vent is directly over a test bench one day and you move it and it's not the next day, that actually does have a big impact. And two is ambient fluctuates, of course, because the thing's going to toggle on and off throughout the day, whether it's heat or forced air or AC or whatever, that impacts things. And there's really only one good way to control for that, which is going to be active logging of the ambient temperature. So as we've discussed before, we use thermocouple readers. There's a whole list of caveats with these as well. I'm not going to go into. These do take some training, but you use a thermocouple reader, you log the ambient temperature. Ideally, you also, if doing internal testing like Kyle did, would log the internal case temperature as well, and you do that on a second-to-second basis. So the idea is to create a giant Excel file, and it's work, but it's really accurate. You create a big Excel file. One column is the ambient temperature you've logged, other ambient temperatures or probes you've logged go somewhere else, and then you have your CPU column for either package or core, whatever metric that you trust from the software, and that's a whole different thing too. So once you've created that, you can create a delta value, and this helps control for the fluctuation in ambient, whatever is happening up there from the ceiling vents or floor vents or whatever, you can control for that. That helps, but it doesn't fix all problems. And there are plenty of things there that are not quite so straightforward either, but we did discuss that in one of our previous videos. I'll put it in the description or something. So thermocouple readers help. We use K-types. They have about a 2.2 degrees Celsius range. If you're using multiples, you will want to calibrate them. Put it in ice water, put it in boiling water, see what the temperature difference is, and then you create an offset in the spreadsheet and just build a template around that. The next thing is really just BIOS. So CPU, the things that matter here when using an Intel CPU especially, it's important to disable basically everything. You disable C states, which are power saving states, disable EIST, speed step, speed shift, anything like that, disable turbo boost, then lock the frequency to a fixed frequency for all cores, and then lock the vCore as much as you can. And motherboards do have variants here. So the motherboard really matters a lot. As we showed in our 7700K review, you can have upwards of 20 to 30 degrees Celsius swings if using auto vCore with different motherboards, and even fixed vCores that you've configured. So fix all the voltage settings you can for the CPU. We do 1.28 or 1.275 depending on what particular cooler and CPU and bench we're working with. And that will fix almost all the problems immediately. So the reason that is because when you have a CPU, an Intel CPU says, I am going to boost as much as possible when thermals allow and when voltage and power supplies allow. So let's say the CPU is boosting. Occasionally, it will either have, you might have V droop, whether that's from your voltage and power supply chain, or you could have just a frequency drop and voltage change up or down based on whatever's going on with the test process. And then, of course, AVX instructions also can really change things. So make sure you understand what those are too, if using Prime 95 or something like that. But with the voltage supply, basically with the Gigabyte board we tested, you can see the voltage go up to 1.4 and then fall to 1.28. And if it's doing that throughout a test process, the temperature is going to be all over the place. And if you're averaging over, say, 1,000 cells of data, it's just not going to be reliable. And I can say that confidently because I've gone through that and I know how difficult it is. You're sitting there pulling your, in my case, many hairs out, wondering what the hell is going on? Why is this configuration that's clearly superior by all measures doing worse than this other one? So like an example would be if you tested two same company products, maybe a 280 versus a 120 even or something like that. If you see temperatures that are really close or unreliable, it's probably because of vCore and CPU settings. So all that needs to be fixed or turned off. And for anyone who says, well, then the CPU is not a real world scenario anymore because now it's not out of box, why would you test that way? Well, the reason is with thermal testing, we're not doing a CPU review. So you don't care about how does the CPU do these functions. All you care about is how do I make the CPU a steady state? How does it do one thing, generate heat, and do that one thing with exceptional accuracy and make it reproducible every single test? The answer is turn all of that power saving shit, all the turbo boost and all that stuff off and fix vCore. That fixes most problems. Next thing, fans. So the fans in the bench, whether it's open air or in a system, they should be connected to the power supply, and it should be a power supply with a voltage that you really trust, because if there's fluctuations, again, if it's a cheapo power supply, it might swing from something like 11 to 12 volts, and that does change the fan speed. So that's important to know. I don't trust the motherboards generally to control my fans for me. Some of them do it just fine, but we've had too many issues in the past, so I go straight to the power supply. And what else can we do here? Software, my bold note on the sheet, software can't be trusted. And it's true for a lot of things. AMD, for example, if you're running AMD CPUs for your thermal benchmarks, good luck, because they use a different temperature scale, TCTL, and your temperatures with AMD for FX and FM CPUs, it will look like it can idle below ambient. That is impossible. It is not physically possible to have a lower temperature than ambient with any of these coolers on the table, whether it's air or liquid. And that's because the temperature that is ultimately being pulled through the radiator is going to be the ambient temperature. So it's impossible. So if you see temperatures that when you produce a delta value are negative, that means something went horribly wrong It could be a negative 0.5, and that might be a calibration thing with one of these, or it could be negative 5 or negative 10, and that's wrong. It's not possible. So that's an AMD thing, and that's not just AMD, it's the software. With Zen, this might change, but software pulls data from sensors in the chip, and you need to understand what values can you trust. For example, with Kaby Lake, it was kind of difficult with all the core temperatures and things. The software didn't work quite the way it has in the past for the immediate versions anyway. As they update, it might change. But for Kaby Lake, you want to use CPU package through hardware monitor because that's the same as XTU, which is obviously trustworthy because it's an Intel utility. So that matters. Make sure you understand which metric you're using and stick with it, whether you're taking all 4 cores or whatever and averaging them, or whether you're taking CPU package. I don't use cores with Kaby Lake. I use CPU package from hardware monitor or from Ada, and then just check it with XTU and make sure you're safe. So that mostly covers software can't be trusted as my bullet points. Software is also really important though. Once you've got a base understanding of it, turn on logging, run it for the entire test, and generate logs for everything because it doesn't hurt to have more data. So we generate logs for CPU frequency, CPU utilization, I'm talking about this cooling testing obviously, vCore, all the voltages, all the power draw measurements, sometimes it's accurate, sometimes not, depending on the software and the CPU, and temperatures, and then dump everything into a spreadsheet. And the idea is when you do have one of those scenarios where you're like, what the hell is going on here? I don't get it. You look through the logs and you can say, oh, why did the frequency just drop from 4.4 to 4.0? That's a problem. And so then you know where to start looking for the root cause. So log files are critically important for that. And there's a lot of other stuff. To kind of quickly go through the rest, multiple tests in the same location with the same configuration are important. So before embarking on any kind of cooler or thermal testing, build the test platform, change nothing, after obviously applying all these settings, change nothing, and run the same thermal benchmark, whether you're using Prime 95 or whatever else you want to use, Ada or any of those tools. Make sure the test runs are sufficient length to warm up and saturate the cooler and figure out where you're going to start averaging for the load and the idle temperatures and things like that. And once you've run that test enough times, look at the data and try and understand, is it the same? What is my variance? And if you've got a variance of about a degree and you can't get any more accurate than that, which is possible, then it's time to add a little note to the charts and say, my temperatures have a variance of plus or minus 1 degree Celsius. And so then you can say, if we've got a cooler that's measuring at 51 versus another one at 52, they are effectively identical. You cannot do any further validation to prove that one is better than the other. And of course, functionally, they're basically the same anyway, even if those hard numbers are accurate. But if you've got a 1 or minus, plus 1 minus 1 degrees Celsius change, then just I make a note of that, of course. Ours is 0.5 or so after calibrating for the thermocouples and all of that stuff. The test environment matters too, so that would include things like thermal paste, open versus closed air. I'm not going to go into that today. There's a couple other things, GPU load, things like that. So let's go back to Kyle's situation. Kyle was testing in a system and he was using a utility that loads both the CPU, the GPU, and some of the memory. That was Unigen Heaven. And so when you're doing that, the potential thing to look out for is GPU workload, because now we could do all these controls I've already listed for the CPU, but now if you're involving the GPU, it gets a whole lot more complicated. We don't involve GPUs for cooler tests. For his test, it made sense. But you have to control for, one, it's got to be the same video card. So if you're changing coolers, pick a reference board, pull the reference cooler off, put it on whatever you're testing, use the same card, and then you've also got to control for, of course, like the frequency. You have to control for boosting. If it's a Pascal card, good luck. That's a lot more difficult. Control for voltage, fan speed, power draw, and temperature thresholds and things like that that could impact performance. Ideally, you fix the fan speed on the GPU. Ideally, you fix all fan speeds, which if I haven't mentioned it yet, that's the next most important thing after CPU voltage is every fan you must have a fixed speed for. No variance, no smart CPU fan header, no letting Windows or BIOS or the motherboard or the fan controller or the built-in software for the cooler try and control the fan speed. that ruins everything. You can do those tests separately, but not for the main benchmark. But back to Kyle's stuff. So GPU, the back of the GPU can radiate heat. When we tested the EVGA cards for VRM temperatures, we saw that we were able to get the backplate of one card up to something like 130 Celsius when we really, really, really tortured it beyond any reasonable measure by dumping 40 or 50 degrees Celsius air straight into the VRM fan from a liquid cooler. So the point is, the back of the GPU can radiate a lot of heat, and depending on how your cooler is oriented, that can impact the CPU temperature. Now, that's a valid test environment. That's a valid thing to look for, but it's got to be controlled and understood. So the example would be if you are radiating heat off the back of the card and you flip the cooler so that it is now oriented this way, it could be sucking hot air in through here, and that would actually increase your CPU temperatures because you're now you're pushing more heat through the cooler, and it's only got so much it can handle before it's kind of saturated. So that's something to look out for. Basically control GPU and everything else in the system. It's really annoying. Every single thing has to be fixed, and you've got to log it, run the tests a million times, and make sure you understand the variance for each particular component. Pretty annoying, but great once it works. Thermal paste. So we have thermal paste from the same batch that we know, same conductivity. All this is getting really, really gritty, not necessarily that important compared to all the rest because the variance is going to be small here, but once you've already done all the other work for all this other stuff, you might as well. So we use, with liquid coolers, thermal paste applicators. This makes sure that, and we've got a video on it, when we apply the thermal compound to any liquid cooler, it's exactly the same. It's equivalent to coming straight out of a factory. And then fixed application method for your air coolers is important as well. And of course, there's all kinds of other variables. Curing time, technically paste can cure. We don't really account for that. That is one variable I don't care about right now because I've tested and it's not important versus all the other stuff to worry about. I think that covers the basics. Anyone thinking about thermal cameras, we've got a whole video on all the problems with using one of these. They're great tools, but it's another thing that you got to understand what it's doing. So I think that goes through most of it. I will add as many images and things as I can to this video. As I said, it's a Sunday video, which means I'm producing it myself. So hopefully just the knowledge will help. If anyone out there finds this useful, please, if you're a content creator, just let folks know that we helped out, because this has been many years in the making. It's been very expensive to develop the methodology, and sharing it is you keep something secret, but sharing this much, if it's helped you, please just let folks know and point them our way. So thanks for watching. If you have any questions, I suppose submit them on the Ask GN videos. I check those every week. Tweet at us at GamersNexus. Subscribe for more. Patreon link in the post-roll video or at patreon.com/GamersNexus, gamersnexus.net for the site. I'll see you all next time.